Righty, my name is Logan DeShepper. I'm in Physics 105 with Dr. Sean Bartz, and today I'm going to be explaining how position, velocity, and acceleration changes as we throw a ball directly up into the air and catch it as it falls down at the exact release point. So the first step we're going to do is draw a picture of how all of this is working. And so right here we have me, and we're defining upwards motion as positive and downwards motion as negative. And so that's going to be really important as we draw these graphs because both velocity and acceleration are vector variables. And what that means is while we assign a number to it, it's also important to consider how we define distance because it changes the signs of both velocity and acceleration. And so the first step I want to do is point out some important things in this picture. First off, this is the highest point the ball travels. So for an instantaneous moment, the velocity of this ball is going to be 0. It just stops in space before it begins its descent. And so I'm labeling this as h. And so as we go through each of these graphs, I'm going to point out just how h impacts this. Alrighty, so for the first one, we're defining position graphically for this scenario. And so position is going to be the distance away from the starting point. So the starting point is here where we first throw the ball, and it's also the end point. And so this is going to give us a parabolic shape for position. So this increasing part of the curve is as the ball gets farther away from us because position is increasing. And so h is going to be the highest point of this parabolic curve. And so also the ball is naturally going to have a descent and lose or become a lower position away from us. And so that's represented by a curve on the right side coming down and approaching 0. And yeah, it's a curve, not a line, because we're losing speed as we throw the ball up and we're gaining speed as the ball falls back down to us. And so that raises the question, how do we actually graph those differences in speed? And that's where a velocity graph comes in to play. And so I think it's a good idea to break this into segments. So first we're going to graph velocity for when the ball is thrown. It's going to have a positive y-intercept because we have the most speed when we first throw the ball. So at t0, when we first release the ball, we're going to have the highest velocity. And so we're going to lose speed as the ball progresses up into the air until it hits the instantaneous moment, h. And so at that point, velocity is 0 because the ball has stopped in space. Now, one of the questions I think about myself is how is this ball going to change speeds as it falls back? And we can think about it, and we know that as objects come back down to us, generally speaking, they're going to increase in speed unless they have some sort of braking mechanism or something like that. And so this is defined as negative motion. So even though speed is increasing, it's represented by a negative line because velocity represents not just speed, but direction as well. And so this gives us a negative line. And again, it's broken up into the throwing portion and the falling portion, and h is where the ball stops in space. And so the next question we have is, how is acceleration changing throughout the entirety of this? So I have acceleration on the y-axis and time on the x-axis. And we know this is going to be a constant acceleration because it's constantly increasing and speed is constantly decreasing throughout its entirety until we hit the highest point, and then speed picks back up, but it's negative because it's representing direction. And yeah, so that part kind of confuses me. I like to think of it as a formula. So the formula for this is acceleration equals final velocity minus initial velocity divided by time. And so if you were to take the acceleration for the throw portions and fall portions with the numbers I've assigned, 4 being the time for when we catch the ball, 4 seconds, 0 seconds when we first throw the ball, and the highest point being at 2 seconds, with initial velocity of 2 and final velocity of -2. If you were to go through and actually calculate that, slope would be m equals -1 for both portions. and that's how you can prove that acceleration remains constant throughout its entirety.